Welcome back with Articosa. So proceeding with the argument of a complex number. So the argument of a complex number, it depends on how our complex number is defined, because our complex number can be defined on the real axis where our z can be only given by the real part only. If you can see, your x is not 0 but your y is 0. So what happens if x is less than 0? If x is less than 0, we have an argument of a complex number z as pi. And also, if x is greater than 0, we can either have the argument of z as 0 or 2 pi. But we're used to the 0. We'll use 0 instead of 2 pi, but 2 pi is also a solution. So the reason being is that the argument of a complex number is not unique. On the imaginary axis, we have z equals to yi. Can see that x is 0 and y is not 0. So if your y is less than 0, with the argument of z is negative pi over 2 or 3 over 2 pi. But for us, we'll use negative pi over 2. And also, if y is greater than 0, the argument of z is pi over 2. So now, what happens if our z is defined on one of the quadrants? Remember, we have 4 quadrants: the first quadrant, second quadrant, third quadrant, and fourth quadrant. So what happens if z is defined on the first quadrant? So it is clear that x is greater than 0 and y is greater than 0. In fact, both x and y are greater than 0. We can have 2 and 2 as an example. So our z can be defined by 2 plus 2i. So we'll measure the argument of a complex number as the angle from the real axis to where the complex number is defined. So I'll name this angle A, and I'll take it as the reference angle for other quadrants. So on the first quadrant, my argument of a complex number is always defined by the tan inverse of y over x for both y and x being greater than 0. And for z being 2 plus 2i, it means the argument, which is theta, is tan inverse of 2 over 2, which is the same as tan inverse of 1. We get the argument as pi over 4. So what happens now if it is defined on the second quadrant? I can have negative 2 and 2. So complex number z can be defined by minus 2 plus 2i. So the argument of z in this case is an angle that is from the real axis to where my complex number is defined. So if we can check. So from here to here is pi. So in the second quadrant, we'll always define the argument of z by pi minus a, where this angle will always find it on the first quadrant. So this will be referred as the reference angle for the other quadrants. So for the very same problem, we're having minus 2 plus 2i. When I find the argument, I have to find angle A first, then I'll say tan inverse, as I did here, 2 over 2, regardless of what sign am I having here. I don't include this negative. So I'll still get pi over 4. So which means the argument for this one is given by pi minus pi over 4. And I have my solution as 3 over 4 pi. So in the second quadrant, that's where your x is less than 0 and y is bigger than 0. So the argument will always be defined by pi minus a, where this angle is the reference angle. And if you can look at this line of the imaginary axis as the mirror, this angle can be reflected this side. So that's why we are determining an angle from here to here, and we know that here to here it's pi, so which means to get this angle we say pi minus a. So in the second quadrant, this is always the case. Now let's see what happens when both x and y are less than 0. And that's when our complex number is defined in the third quadrant. I can have -2 and -2 as my example. So my z, it is clear that it's given by -2 minus 2i. So the argument of z, it will be defined by an angle from the real axis to where my complex number is defined. So here in the third quadrant, it's either it can be a minus pi or a plus pi, but we're used to this one. So that's how the argument is defined. The angle, we still find it the same way as we did in the first quadrant. So it's already pi over 4 for this problem. We're just looking, remember we take this but without the signs, we take only positive. So we reflect it on the first quadrant. So if we reflect this point on the first quadrant, this is the point. That's what I mean. So it depends on the complex number. So if, for an example, I was having my z being defined by -1 minus root of 3i, I was going to reflect on the first quadrant my point as 1 and root of 3. Then I find the angle A. That's when I will find the argument by just taking that angle minus pi or that angle plus pi. So for A, it will be the tan inverse of root of 3 over 1 for this problem. So this is pi over 3. So the argument of z for this problem, I'll find it by theta is given by pi over 3 minus pi, which is -2 over 3 pi. So this was just a demonstration so you can understand what's going on here. So for this problem, now your z is -2 minus 2i. Your argument already, you can see here, it's pi over 4. So to find the argument for this one now, you're going to take the pi over 4, you subtract pi. You'll find your solution as -3 over 4 pi. And that's it. I think I have done a very much clear demonstration. So on the fourth quadrant, which is the last quadrant, now you can see that your y is less than 0, but your x is bigger than 0. I can have 2 and -2 as the example. So if you can check below this line, the real axis, if this is my angle A, here I'll reflect it as -a is below. And the angle which I'm looking for on the fifth quadrant, I'm measuring an angle from here to where my complex number it is defined. So the argument of complex number is either given by -a or 2 pi minus a. But we are used to -a. So for this very much problem, you can see your z is defined by 2 minus 2i. It means that the argument of z is given by -pi over 4. Thanks for watching, and please keep on subscribing and supporting, and I have more videos coming for you, so you're welcome.